Welcome, Lesson 7. I want to give you a quick overview of statistics. And so some of the objectives here to learn, explain the difference between a population and a sample. Now, statistics is really the description of data. So we're going to talk about how to, different measures of the location of where the data is, how dispersed the data is, how skewed the data is, and then some measures of what we call association. Can we associate the data? So, if we talk about measures of location, we're trying to describe the data to somebody. And one of the first things most people are going to want to know is, well, where's the center? Where's most of my data? Where's the majority of my data? What's the middle point, right? Well, we got three key measures of that, where the location is. The first one is called the mean, or as most people call it, the average. You add up all the scores, add up all the test scores, divide by the number of test scores, and that gives you the average. Or in Excel, there's a function key just called average, and of course you have to give the data range to Excel. You have to say the average over this data range, and Excel will automatically give it to you. So the average is the mean is the average, sometimes is expressed as x bar for a sample, mu for a population. The median is the middle score, which is the one in the middle. So I line everybody up in the middle score, or the middle person, the middle height. That's called the median. And again, Excel gives it to you, median, tell it the data range. The last measure of location that's typically used is the mode, which is the most frequent score. And again, you can say mode single, and the reason for single is most people, you can get into distributions that are bimodal, which we'll get into later, but this will give you the mode, the first one Excel finds in the data range. So the purpose of all these measures of location is to tell us where the majority of our data is, what the mean, the median, and the mode is. And that's a great first step in describing data. Now, the next step might be I might want to know how dispersed my data is. How far away from the range, from the mean is my data. So first step, I might want to look at what's the range of my data, right? That's just the difference between the highest score and the lowest score. So in Excel, we could say, give me the max. Again, I got to tell it the data range, minus the minimum score. So the test scores, the lowest score was a 50, the highest score was 100. Tells us something about the range, tells us something about how dispersed our data is. The next one that we've got a special video, the next three we've got sort of subset videos for to go into a little further explanation of. The next one's called the standard deviation. It says, well, how far away from the mean is my average test score? And we'll show you how to do that. The next one is a z-score, which says, well, okay, how can it allows you to take a test score minus the mean divided by the standard deviation to put it on a common platform. Because if I told you that I had a test score of the standard deviation on SAT scores might be 100. The standard deviation on a test score we might have in class, because it's out of 100, might be 10. Well, because the SATs are out of 1,600, maybe a little higher now that they do 3, it's hard to compare one standard deviation of one data set to another data set. Well, that's what the z-score does. The last thing is coefficient of variance, which basically says, well, the standard deviation is what percentage of the mean. That's another way of comparing two different size data sets, right? So if the standard deviation is 20% of the mean versus a standard deviation is only 10%, well, the one that's 20% is going to be more diverse than the 10%. So let's go into the standard deviation. Here's this intimidating formula, but we're going to walk you through it, so hopefully you'll understand it. Hi, I'm going to walk you through one of the key measures of dispersion in statistics called the standard deviation. And here's this very intimidating formula for what standard deviation is. But let's walk through it, and I think we'll find it's not nearly as intimidating as it looks. So let's make up three test scores, an 80, an 85, and a 90. And we're going to need to know what the average is, so we can come up here to Excel and hit the function key, say tell us the average. It's going to ask us for a range. We want that range, and not surprisingly the average is an 85. All right, now one of the standard deviation, the key measure of dispersion is we're trying to figure out how far away from the average, or the mean, which is this X bar, it stands for the mean, how far away from the mean are our scores, or how dispersed are they? So, not surprisingly, all we have to do is take the difference between each test score and the average, or the mean, right? And I'm going to lock in Excel, remember our lock keys, our dollar signs. And now I can fill this down, and because I have very few, I'm just going to add these up. All right. So I get a dispersion of 0. Well, wait a minute. It doesn't make sense. Obviously, I can't have a deviation of 0 because that would mean all my test scores were identical. So obviously, we're doing something wrong. Well, what are we doing wrong? Well, we're taking each test score, subtracting it from the mean, and adding them all up. And what's happening, if you think about it, not too surprisingly, is our negative numbers and our positive numbers are negating each other. So, of course, if we take all of our test scores, compare them to the average, and add them all up, we're going to get right back to the average, or 0. So, to compensate for that, what the formula does is squares each one of these numbers, right? Because what happens when I square a number, if you remember your math, if I take each number and I square it, it turns negatives into positive, because a negative times a negative is a positive, right? So now what I've done, if I sum them all up, now I actually have a positive number, because notice the negative 5 has become a positive number, and now I've got something here, okay? Now, the next thing I want to do is, obviously if I had 100 test scores, I'd have my summation would be much larger. So what I want is, I want the average deviation. So I take my sample size minus 1, which is 2, right? And now average, I just take my 50 divided by my sample size minus 1 to make this an average deviation, so to speak. Now, I have an average deviation, how far I'm deviated from the mean, but remember I squared all these numbers, right? So someplace in here I got to unsquare them, which is this guy, the square root. So now I can take this number, take the square root, or raise to the 1/2 power, and I have 5 as the standard deviation. Now, we've sort of walked through why this, at least to me, makes a lot of sense. I take each test score, compare it to the mean, square it to make it positive, sum them all up, divide by my sample size minus 1 to get an average deviation, and then take the square root of that number. Now, lucky for you, you don't have to go through all of this, because Excel, if you go to the functions, and you go to statistical functions, and you come down here, and you go to standard deviation S for a sample. It's P for a population, but we're doing with a sample. It says, tell me the numbers. And I say, okay. And whoa, I get 5. Hope this helps. It's a measure of dispersion. It helps us describe our data, how far away from the mean our data is. Thanks. Okay, now let's understand what a z-score is. So what a z-score is going to attempt to do is tell us how far away from the mean is our one specific score. But then if you think about it, if we wanted to figure out percentages, we'd have to have hundreds and hundreds and hundreds of tables. So what it's going to do is it's going to take the difference between our score and the average and divide by the standard deviation for that sample to give us a z-score, which will be a common score normally from a -3 to a +3 because we know 98, 99% of our data falls between plus or minus 3 standard deviations of the mean. So what a z-score is really doing is it's saying, all right, let me find out how far away from the mean my test score is, but so that I can go look up those percentages or percentage of what percentage of my data is going to fall in that range, or where on a percentile rank an individual score ranks, I'm going to divide by the standard deviation so that I can have one set of tables, one set of z-score tables that I can go look it up. Now, luckily for you, again, in today's world, you don't look up tables. Excel's going to give it to you all. But I'm trying to have you understand sort of a little bit about the background of this. So if we take the same test scores we had a minute ago, we sum them all up, and we calculated a few minutes ago that the standard deviation is 5. If we wanted to find the z-score for each one of these, we would just simply come in and we would say, well, how far away from the mean is this score, right? And I'm going to put parentheses around this and lock in my and divide this by the standard deviation. And I want to lock that before I copy it also. So I get a z-score for the first one of a -1. What this is telling me is I'm -1, the score of 80 is -1 z-score away from the average of 85. And a negative means it's a lower score. The 90 is 1 z-score above the mean. All right? Now, if you didn't want to do this arithmetic, lucky for you, again, there's a equation within Excel. You go up to functions. Again, you go to the statistical. You go down to standardize. And you say, okay. It's going to ask you, what is your test score? What is your X? 80. What is your mean? Right there. Now I'm going to have to lock this in so that I can copy it. Asks us what the standard deviation is. We give it to it. To make it easy to copy, I'm going to lock it in again. And check OK. And now I can fill these down, and it's already done for us. So that's what a z-score is. All right? So what a z-score is doing is it allows us now, there'll be tables where we can go look up what percentage this range, where this data falls. Z-score is basically standardizing each one of these by taking the individual score, comparing it to the mean, and dividing by the standard deviation. Now, the last piece is called a coefficient of variance. Now, this is where I have two different populations, all right? It's going to take the standard deviation divided by the mean times 100. And don't memorize them all. You can look them up, but I want you to have an understanding of why they exist. So a coefficient of variance is really there to say, well, what if I have two sets of, let's say you took two tests. The first test, the average was a 60 and the standard deviation is a 12. The second test score was a 72 with a standard deviation of 14. Well, and I said, well, which test score was more diverse? Which one was a larger? And you said, well, obviously test score 2 because the standard deviation was 14 versus 12. Well, maybe yes, maybe no, because notice the average was much higher, right? So maybe test 2 is less diverse than test 1. So what a coefficient of variance does is it just simply says, well, what percentage is the standard deviation of my mean? So it takes 12 divided by 60 and says, this basically says my standard deviation is 20% of my mean. Test score 2, the standard deviation is only 19.4% of of the mean. So the reality is, when I put them on a sort of even playing field by using the coefficient of variance, actually test 2 was less diverse than test 1, even though it had a higher deviation, because its coefficient of variance, the standard deviation as a percent of the mean was lower, therefore it was less diverse. Hope this helps. If there's any questions, let me know. Okay, I want to show you how easy, what you're really most likely going to do. You're not going to go down each one of these stats one by one. What's most likely you're going to do is there's an add-in called in Excel called Analysis. So if you go to Excel Options and you say Add-ins and you say Analysis Toolpak, and you say Go, and you can see I've already checked these boxes, but you may want to check them. And what that does is when you open up data, you get this little data analysis tab, which is very handy because now all I have to do is say, analyze this data, give me a bunch of descriptive statistics, so a bunch of other things you're going to be able to do, correlations. But for now, let's just give us the standard descriptive statistics. It's going to say, well, what range do you want? Well, this range of data here. Where do you want to put it? Well, we could put it in a new worksheet. We could put, I chose an output range. Well, let's show you. Let's put it right here. Okay. And I just check summary statistics is what I want. And so what it's going to do is it's going to give me all those statistics, common statistics that we've talked about for these range of data right there for me, right? So it gives me automatically, I get the mean, which we knew was 85, median in 85, standard deviation of 5, sample variance. Kurtosis is 0 because we're dividing, this is a perfectly bell-shaped curve. We have no skewness. Again, it's perfectly bell-shaped. Our range is from 80 to 90 or 10. Our min is our max. Summation of all of them and the count, the number. So basically, in one click, we get all the standard statistics, which is what you're going to want to start doing most likely rather than each statistic. Just wanted you to be aware it's there. Okay, let's talk about a couple more ways that we might want to describe data to somebody. And we might want to describe the shape of our data. So our data, if you think about our data could be very steep, or it could be very flat, or it could be skewed to the right of the mean, it could be skewed to the left of the mean. So a couple measures that aren't too frequently used, but I want to make sure you've got them in your toolkit. First one is called Kurtosis, which is a measure of how flat or how tall our data is, right? So if you get, and you can do it in Excel, it's called a Kurt, and you give it the range. And if it's less than 3, it's very flat and very diverse. And if it's greater than 3, it's very tall and very less dispersed. The second measure of shape is sort of how a coefficient of skewness. So if it's skewed to the right or the left of most of our data, is the mean to the right or the left of the majority of the data, and that you can get with skew data range. Again, these are two typical statistical measures of the shape of our data. The next item, and that's very important, is measures of what's called association. So now what we're doing is we're pulling in, and now statistics becomes very powerful. What if we had two, and you'll see an example in a minute, what if we had two sets of data and we ask the question, gee, I wonder if as one varies, the other varies. And then we may get into even things like cause and effect. Two big measures for that. One's called the covariance, which is to see if the two are associated, and there's an Excel function for that. And the other is a correlation coefficient, which puts it on a common platform so that we can see are two sets of data associated with each other. And you can see the ramifications of this are enormous. Is study time related to grades? Is the amount of TV I watch related to obesity? Is the drug I take improve my blood pressure? All sorts of things that bring into the power and the importance of statistics. So now we're going to show you a little bit of how these work, how the equations work. You don't need to memorize the equations. The equations are all in Excel or any tool that you use, statistical tools. But in this video, I'm going to walk you through the formula, not so you memorize the formula, but for you so that you have a background understanding of how these things were developed and the rationale, so that you hopefully have a deeper understanding of the statistics. Any questions, let me know. Okay, now we're going to try to figure out if two sets of data are associated with each other or correlate to each other. And again, these formulas look incredibly intimidating, and my only purpose for showing them to you is to sort of break them down so you have an understanding of what's going on, so that when you click on the Excel tool, you sort of understand what's going on. So let's think about, let's think 3 examples. Hours of study and grade. So, I would sort of think these might be correlated. The guy or gal that studies 3 hours might get a higher score than the one that studies 1 hour. And these intuitively look like they might be correlated, or associated, but let's prove it. So the first thing we look at is what's called the covariance, which is this fancy equation up here. But let's break it down and let's think about how we could figure out if two numbers are correlated to each other. Well, the first thing we're going to do is we're going to take the first set of numbers and we're going to compare it to the mean, which I've done right here. Study, so that's my 80, my study hours 1 minus the average of 2, so I get a -1, 2 minus the average, and on down. And then I did the same thing for grades, and what I'm trying to look for, and that's this first part of this formula right here, and multiply the two together. So if we sort of think about what's happening, we're saying, hey, if this one's negatively away from the mean, and they're associated with each other, in other words, they go in the same direction, then this one will be sort of negatively deviated from the mean, which notice we've got that right here. And notice the other neat trick, when we multiply them together, we get, our two negatives offset each other. And, if you think about it, if we got a positive and a negative, we want this to be sort of negative because that would mean they're not associated with each other. In other words, if this one was positive to the mean when this variable was negative to the mean, by multiplying them together, we sort of get that, what we want. It becomes a negative. But if they're kind of floating in the same direction, either both positive or both negative, when we multiply them together, we get a positive number. So again, we sum them all up, and we divide by our sample size -1, which is 2. So we get a covariance of 5, which again, you can go out on Excel, and Excel has this, and it'll calculate it automatically for you. You just put in the function COV and give the range, and it'll give it to you. So now we have 5, but that really doesn't mean too much to us, right? Because if you think about it, different sample sizes are going to have different standard deviations. So, and notice here we got a standard deviation of 1 for study and 5 for grade. So if you think about it, in a perfect world, if they were perfectly associated with each other, this would vary by 1 every time this one varies by 5. Well, here's our R stands for our correlation coefficient. So what we're doing is we're taking the correlation equation, and then we're basically dividing by this thing that looks very complicated. But if we remember, all this is the standard deviation of the one times the standard deviation of the other. So what we're kind of saying here is, if we got a correlation of 5 and we divide by the standard deviation, that'll tell us if how closely they're correlated. Now, a correlation coefficient of 0 means they're very not correlated at all. A correlation coefficient of 1 means they're perfectly correlated. and something in between will tell us how closely they're correlated. But all we're doing, and again, you've got all of this, Excel will calculate it all, it's one of the formulas. But what we're really doing, and it's kind of neat, is we're saying, well, how far when this one varies from the mean, this one should vary from the mean in the same direction. And if I divide by the multiplication of the two standard deviations, that's how I come up with my correlation coefficient. Hope this helps.